on topic list structures. So today our agenda is understanding list in data structures, implementations and applications of list, advantages and limitations of list. In computer science, data structures are essential tools that helps us organize and manage data efficiently. One of the most fundamental types of data structures is the list. Lists are widely used in programming and algorithm design because they allow us to store collections of data in an organized way. So, what is a list? A list is a linear collection of elements where each element can be accessed in a specific order. You can think of it like a row of items on a shelf where each item has a designated position. List can hold various types of data, including numbers, strings, or even other data structures. So, types of list are singly, doubly, and circular. What is it? A singly list is a collection of nodes where each node contains two parts: the data structure, the value we want to store, and the pointer or reference to the next node in the list. How does it work? The first node is called the head and it points to the second node. Each subsequent node points to the next one, with the last node pointing to null, indicating the end of the list. So its key features are one-way traversal, and its common operations are insertion and deletion. Second one is doubly linked list. What is it? A double linked list is a similar to a single linked list, but each node has two pointers, one pointing to the next node and another pointing to the previous node. So how does it work? This means you can move in both directions, forward and backward to the list. Its key features are its two-way traversal and more memory use. Two-way traversal, you can go back and forth, making some operations easier. More memory use, each node needs extra memory for the additional pointer. Common operations, insertion and deletion. Third one is circular linked list. So a circular linked list can be either singly or doubly linked. The key feature is that the last node points back to the first node, forming a circle. So how does it work? There is no null reference at the end. You can keep traversing the list continuously. Key features: endless traversal, flexible size. Common operations. Operations are similar to singly or doubly linked list, but you must handle the circular nature while traversing. When to use? See, circular linked lists are ideal for applications like round robin scheduling, where you need to keep cycling through tasks or process. So let's discuss the common operations you can perform on lists in the data structures and algorithms. In a way that's easy to understand, we'll cover the basic operations and explain how they work. Insertion. Insertion involves adding a new element to the list, where you can insert at the beginning. This is often the fastest operation, especially in linked lists. For example, if you are managing a to-do list, adding a new task at the top of is quick. At the end, adding the end of the list can be fast in an array list if there is enough space. In linked list, it may require traversal to final the last node. At a specific position, you can insert at a specific index, but this usually involves shifting elements in an array list or traversing nodes in a linked list. Time complexity. Singular linked list at the beginning, O of n at the end or middle. Doubly linked list, O of 1 at the known positions, O of n otherwise. Array linked list, O of n if inserting in the middle, O of 1 at the end of an average. Traversal is going through each element in the list to access or process it. How is it done? Iterately using loops, you can access each node or element in order. Recursively, you can also use recursion to visit each node, especially useful in linked lists.
Myself, Reshma, and my registration number is 941. So I'm going to tell you about visual representation of list structures, graphical node connections. When we talk about lists, especially linked lists, it's helpful to visualize them. Typically, nodes are represented as circles or boxes with arrows showing how they connect to one another. How they connect to one another. Each node contains data, the information you want to store, and a reference or a pointer. to the next node in the sequence. This visual and aids helps us understand how data is organized and how we can navigate through the list. For example, in a singly linked list, you will see each node point in the next node, ending with a node that points to the null. In a doubly linked list, each node points to both to the next node and the previous one, allowing for two-way navigation. In circular linked list, the last node points back to the first node, forming a loop. Implementation and application of lists. Linked lists. Structure and use cases basic structure overview. A linked list is made up of nodes, where each node contains data and a pointer to next node. This allows for dynamic memory allocation, meaning the size of the list can grow or shrink as needed without needing to prelocate memory, like in arrays. This flexibility makes linked lists ideal for applications where the number of elements isn't known ahead of time. Use cases in applications. Linked lists are commonly used in they can easily handle adding and removing elements from each element. Dynamic management. They help efficiently use memory by allocating only what is needed. Graph representations. Lists can represent edges in a graph, facilitating traversal and manipulation, performance considerations. While linked lists provide O1 time complexity for insertions and deletions at known positions, like adding at node and at the head, accessing elements like takes time because you have to traverse the list from the beginning. This makes linked list less suitable for situations where frequent random access is required, such as for searching specific element. Listen, stacks, and queues. How they work stack implementation. Stacks operate on a last in, first out principle, that is LFIO. This means the last element added in the first to be removed. Using linked list, elements are added, pushed, and removed from the top, making these operations very efficiently typically and making these operations efficient. Queue implementation. Queue first in first out, that is FIFO principle, where the first element added is the first to be removed. In a linked list implementation, you can enqueue elements to the back and dequeue from the front, ensuring orderly processing of the task. This setup also since adding and removing from either end can be done efficiently. Advanced applications. Graph and heaps. Graph overview. Graphs are data structures made up of verticals and edges and are used to represent relationships in various applications like social networks or transport systems. They allow for efficient transversal using algorithms, helping find the shortest paths or connections. Heap structure. A heap is a special tree based on that maintains the heap property. In a max heap, each parent node is greater than its children. In a min heap, it's opposite. Heaps are crucial for implementing priority queues and sorting algorithms like heapspot, which efficiently organizes data. Applications in algorithms. Graphs are essential for algorithms that require finding the shortest path, such as Dijakshatra's algorithm. Heaps enhance performance in scheduling tasks and managing resources, making them vital in areas like operating systems and real time systems. Real world examples of list implementations. Social media platforms often use linked lists to manage user connections. The structure allows for dynamic updates like adding or removing friends while efficiently retrieving friend data for features like suggestions and mutual connections. By using linked lists, these platforms can handle the constantly changing nature of social connections with sacrificing performance. Understanding the visual representation, structures, and applications of lists is crucial in data structure. Lists provide flexibility and efficiency in managing data, whether it's through stacks, queues, or more complex structures like graphs and heaps, recognizing their real world applications and importance in software development algorithm design. Now, my teammate Thanvik will continue.
Myself, Tanvik Saurya. I'll be saying about the advantages and limitations of lists, benefits of using lists and data structures, dynamic size adjustment. One of the main advantages of lists, especially linked lists, is their ability to grow and shrink in size dynamically. This means you don't have to decide how many elements you need ahead of time, which is great for situations where data size varies. Efficient in insertions and deletions. Lists allow for quick insertions and deletions. For example, adding or removing elements at that time at the beginning of a linked list can be done in constant time. This makes lists ideal for applications where data changes frequently. Easy transversal methods. Transversing through a list can be done easily using loops or recursion. This straightforward approach allows for efficient processing of all elements. Flexible memory usage. Lists utilize memory more efficiently since they only use as much as space as needed for the data they contain. This contrasts with arrays, which often reserve memory upfront, leading to wasted space if not all slots are used. Supports various applications. Lists are versatile and can be applied in numerous scenarios such as implementing stacks, queues, and other complex data structures like graphs and heaps. Simple implementation of techniques. The basic structure of lists, especially linked lists, is relatively simple to implement. This makes them accessible for students and beginners to understand and work with. Limitations and challenges of list implementations. Memory overhead issues. Over One drawback of linked list is that they require the extra memory for pointers. Each node in a linked list is not only holds data but also a reference to the next node. This can lead to significant memory overhead, especially if you have many small elements. Increased fragmentation can occur, which can degrade performance. Access time limitations. Unlike arrays, which allow for constant time access to elements via indexing, lists require sequential transfers to access an element. In a linked list, this means you may need to visit multiple nodes to find one you want, resulting in time complexity. This makes lists less suitable for applications that require frequent random access. Conclusion: when to use lists and algorithms. Optimal use cases are lists are best suited for situations that need dynamic data management, such as implementing stacks and queues where frequently changes. They enhance the efficiency of algorithms that rely on quick insertions and deletions. Memory considerations. When choosing to use lists, you need to weigh the benefits of dynamic sizing against the memory overhead from pointers. If you're working in an environment with limited memory, this trade off is crucial to consider. Algorithmic efficiency. Lists shine in scenarios that prioritize sequential access and modification over random access. Knowing the specific needs of your application will help you decide when to effectively use lists in your algorithm design. Lists are powerful and flexible data structure with both significant advantages and limitations. Understanding when and how to use them will enhance your programming skills and help you make informed decisions in your coding projects. And thank you.